Thank you very much for the introduction. As already said, I'm going to present you our approach where we use Gaussian processors and neural networks to augment spectral datasets. Higher spectral images are more and more used in industrial applications because they are non-contact and non-destructive. Because in each pixel they contain a whole spectrum and not only RGB data, they have a high amount of information. Often it is the case that there are several substances in one pixel, so spectral unmixing needs to be performed. We do this using neural networks. This has the advantage so that no model knowledge is theoretically necessary. Spectral variability can be considered if it's contained in the data, and constraints for physical plausibility can be enforced by the output layer design. But, as already said today, this only works if we have enough suitable training data. Therefore, one thing we can do is data augmentation. After the motivation, I would like to tell you a little bit about spectral unmixing, so you know what I'm talking about. Then present the approach, present the results, and in the end I would give a short summary. Let's start with spectral unmixing. The aim of spectral unmixing is that you can decompose a spectrum that is measured to get the abundances and the spectra of the pure substances involved. In this presentation, we only are looking for the abundances because the spectra are already known, because they are in the training data set. A classical approach is to use mixing model, so you can do model-based unmixing. An example here would be using the linear mixing model. For physical plausibility, you need the non-negativity and the sum to one constraint for the abundances. Until now, we assumed that one substance can be represented by a single spectrum. This is not true in reality. In reality, we have spectral variability. The main reason in our datasets is the surface structure and the angle in which the light refracts into the sensor. Spectral variability can be taken into account by additional parameters in case of model-based unmixing, or by training data if neural networks are used. Then I would like to continue with the approach. We model the spectra as Gaussian processes in order to involve spectral variability. Those are defined by a mean function and a covariance function. And we have the wavelength as the variable and the abundance vector as additional parameters. And those functions are approximated by neural networks. To get our training data, we take the spectra which have the same abundance vector and calculate the mean vector and the covariance matrices. For the augmentation, we use the trained networks and feed them with additional abundance vectors that are not included in the original training dataset. Then we get those moments and can use the Gaussian processes to sample many spectra for our augmented training dataset. We also looked at the variant of it, where we only use the mean vector. Then we don't have spectral variability in the augmented data, but still in the original training data. Another point for the implementation was how we use those wavelength indices, because the covariance matrices have most of the energy on the main diagonal, and they are symmetric. We use the indices on the right-hand side and not those naive ones on the left-hand side. This way, the neural network can be more simple because it don't have to learn so much changes in monotonicity. The network is shown in this slide. It's quite simple. As inputs, we have the abundance vectors and the wavelength. And as outputs, those values. We use two different networks, one for this and one for that. Then we just a fully connected layer with batch normalization and activation functions. And in the end, we use a logistic activation function. Now I want to come to the results. First of all, I want to introduce the data sets. We captured them in our own image laboratory because we wanted to know the abundances as exactly as possible. The spectral resolution is 4 nanometers, which ranges in this range. It's mostly the visible spectrum. For each abundance vector, we have 400 spectra. That means that each of those boxes has approximately 400 pixels. We use two different kinds of materials to create these data sets, colored quartzons and colored powders. Here we have two different data sets with a different amount of components. And here spectral variability is lower, and here it's higher. This is because here those powders are very fine and they tend to clump together, which makes it more difficult. Maybe you can see it on this picture. On this slide, I want to present a result for the first data set. All 4 experiments were performed with the same neural network with the different data sets or different kinds of augmentation. Here we have no augmentation. Here is an old concept we used where we had a generative CNN, which can do the same as the approach I'm presenting today, but it's much slower, as you can see here. And those are the two approaches. Yes, the approach and only the mean vector approach. And here the colors denote the step size of the augmentation. And this means if it's, for example, 0.2, every possible combination with steps of 0.2 is added to the original data set. As you can see, augmentation improves the results compared to the non-augmented data set, and it depends on the step size, but if it's small enough, it doesn't change much. And the approach presented today is as good as this one, although it's much faster. And even if you only use the mean vector, it's also relatively fast. On this slide, you can see the same diagram for the remaining data sets. If you have more components for the quartzon data set, you can see that the generative CNN is a little bit better, but this still works, and it works quite good. The last data set is the color powder data set. Here the present approach is not as good. Maybe this is due to the fact that the assumption of a Gaussian random vector does not hold here. But still the mean vector variant works. Now I want to summarize the presentation. I presented an augmentation strategy for spectral unmixing datasets. We modeled the spectra as Gaussian processes and used neural networks to obtain the moments of those Gaussian processes for additional abundance vectors. We observed an improvement of spectral unmixing performance if we use datasets augmented by this method. Depending on the dataset, as always, it's almost as good as the generative CNN, but much faster. And if you only use the mean vectors, it still works and it's even much faster. The step size hasn't got much of an impact, but if it's chosen too big, the improvement is not so high. Yes. In the future, it would be possible to use only parts, the relevant parts of the covariance matrices, because we saw that it also works if we only use mean vectors, and those covariance matrices make it slow, and they are very huge, but far away from the main diagonal, there is no much energy, so maybe there is an optimal solution to this. Thank you very much. I'm looking forward for your questions.